Welcome to the deep dive. Today, we are plunging into some seriously cool source material provided by one of you, a research paper titled Masked Manipulator, Versatile Whole Body Control for Loco Manipulation.
That's right. And our mission really for this deep dive is to unpack the core ideas behind creating these virtual humanoids, ones that can not only move around realistically, but also like pick up and interact with objects in a versatile and goal-driven way.
Yeah, it's about bringing digital characters to life in a truly physical sense, isn't it?
Exactly.
And think about how incredibly complex, even simple human actions are. Like you walk up to your coffee cup, right? You reach for it, you grasp it just right, lift it, maybe move it, put it down without spilling.
Yeah.
Doing all of that seamlessly in a virtual world or, for a real robot with both that broad flexibility and precise execution. That sounds like a massive technical challenge.
Oh, it absolutely is. And this paper presents a new framework, MaskedManipulator, designed specifically to tackle that exact problem. It's a system that aims to bridge that gap between, flexible, high-level control and the messy reality of physics and interaction.
Okay, let's unpack this research then and see what surprising insights we can dig up for you. Where did they even begin with a problem this complex?
Well, the fundamental challenge they really identify is creating virtual humanoid agents that are capable of versatile, autonomous, and controllable behaviors, particularly when it comes to skillfully interacting with their environment and, objects.
Right. So it isn't just about walking or just about picking something up in isolation.
No, it's about combining that full-body movement, locomotion, with precise, dexterous manipulation. Hence, loco manipulation. That's the term they use.
Okay, loco manipulation. Got it. And the paper points out this inherent tension, right? You need broad task flexibility, like understanding abstract goals, place the cup here, or reach that point, which are often really vague.
Yeah, exactly. They're underspecified. Versus the absolute need for exacting physical precision. I mean, the source notes this clearly. Even tiny errors during grasping or repositioning or placing an object can lead to failure. You drop it, or the whole thing becomes unstable.
And there's often no easy way back from that failure point in a simulation.
Right. You can't just get close to picking up the cup. You have to get it exactly right relative to your hand, the object's physics, everything.
That makes total sense. The physical world is just unforgiving, and existing methods, they usually focus on one or the other, don't they?
Yeah, typically. Some are great at really sophisticated manipulation for specific tasks, like screwing lids off jars or something very defined.
Or others are good at versatile body control, like just walking to a location based on a goal.
Exactly. But unifying both the full body and the object goals into one seamless, controllable system, that's been a really tough nut to crack.
Okay, so how does Masked Manipulator propose to solve this? What's their approach?
So their proposed solution is this unified control framework, specifically designed for diverse and crucially precise loco manipulation tasks. What's clever is how they build it. They don't try to learn everything from scratch all at once.
Okay, how then?
It's built to be flexible, first off, capable of responding to various inputs, from really detailed kinematic targets like saying, put the hand exactly here at this time, all the way up to those sparse high-level goals we mentioned, like just giving a desired final position for an object.
And you said it uses a two-stage learning approach.
Yes, exactly. A two-stage approach to get both the versatility and the precision.
Okay, what are those stages?
Stage 1. They call it Mimic Manipulator. This stage is all about learning the how. It trains a high-fidelity tracking controller using large-scale human motion capture data. The goal is to physically reconstruct complex interactions within a simulation. Think of it as the expert demonstrator.
Okay, the expert demonstrator, Mimic Manipulator. And stage 2?
Yeah, that's the Masked Manipulator itself. It takes all that intricate knowledge learned by Mimic Manipulator about how to physically interact and distills it into a versatile policy. This is the policy that can generate novel behaviors from those sparse goals we talked about. It's the bit you, the user, would actually interact with.
Fascinating. So stage 1 learns the detailed physics-based movements from humans, and stage 2 learns how to trigger those complex movements using just minimal instructions. Okay, let's dig into stage 1. Mimic Manipulator. How do they train this high-fidelity motion tracker?
Right. Its main purpose is really to reproduce those intricate behaviors needed for dexterous loco manipulation. And they do it by training inside a physics simulation. And yes, they use humans as the teachers.
Using motion capture data.
Exactly. They leverage large-scale human motion capture data, specifically the GRAB dataset. It contains tons of examples of successful interaction strategies, grasping, placing objects, even tricky stuff like regrasping or hand-to-hand transfers.
But wait, raw motion capture data doesn't really account for physics, does it? It's just positions and rotations over time. How do you get a physics-based character to actually replicate that motion and handle real-world stuff like gravity, friction, object dynamics?
Ah, good question. That's where reinforcement learning comes in. They formulate this whole thing as an RL problem. Mimic Manipulator learns the low-level actions, the joint torques needed to accurately execute those human motions, but within a physics simulation.
Oh.
So this ensures the resulting actions are dynamically feasible, physically plausible, and handle all the nuances of object interaction correctly. It operates in what they call a full information setting relative to the reference human motion. Basically, it sees everything it needs from the human data to try and match it perfectly.
Okay, tell me more about the task design for this first stage. What does this mimic manipulator policy actually see? What are its inputs to do this tracking? And crucially, how is it rewarded? What makes it good?
Okay, so its observation, its input, includes the character's own state, where its joints are, velocities, that kind of thing, what they call proprioception.
Right. Body awareness.
Yeah. Plus, object information, where it is, its orientation, velocity, and crucially, relational features, like the vector for each body part to the object's surface. That helps it understand the spatial relationship.
And how does it know the object's shape?
For object geometry awareness, instead of using heavy point clouds, which can be slow, they use something called basis point set, or BPS representation. It's a simpler fixed representation that's pre-sampled. It makes the network architecture simpler and allows for faster training and inference. It's one of those clever technical choices that makes the whole thing practical.
So it knows where it is, where the object is, and kind of what the object's shape is, but in a simplified, efficient way.
Precisely. And importantly, it also observes future reference, poses goals from the human data. Not just for the next frame, but like 30 frames ahead, which is about 1 second.
Ah, it looks into the future of the demonstration.
Yeah, and this includes contact indicators from the human data. So it knows where and when body parts should be in contact with the object according to the human example. Observing the future helps it plan its movements smoothly, which is really key for complex sequences.
That makes sense. Planning ahead. But replicating human motion perfectly in physics sounds incredibly difficult. How do they ensure it's precise enough? You mentioned earlier that little errors can compound.
Right. And this is where they have a really crucial insight, and it's captured in the reward function they designed. As the source notes, minor errors early on, like a slightly wrong grasp angle, can cascade and lead to failures much later. This is a notoriously tough challenge for standard RL reward functions because agents often find ways to cheat or prioritize the wrong thing.
So what's their solution?
Their solution is a multiplicative reward function.
Multiplicative. What does that mean in practice? Why is that so important here?
It means the total reward is the product of several different components. Things like how well it matches the reference pose, how well it matches the reference contact patterns, how much energy it uses to prevent jittery movements, and how smoothly it interacts with the object, like avoiding penetrations.
Okay, a product. So if any one of those components is low, the whole reward tanks.
Exactly. If the pose is perfect, but the contact is slightly off, the total reward is low, maybe even zero. This strictly requires competence in all aspects simultaneously. You have to match the pose and the contact and use energy efficiently and interact smoothly just to get a high reward.
Wow.
It forces the agent to be good at everything, all the time. That's a key insight for getting high-fidelity replication.
Ah, so you can't get a good score by just acing one aspect. You have to nail everything simultaneously. That really pushes for high fidelity and robustness. I get it.
Precisely. And the contact guidance reward, which they show in Figure 2 in the paper, is a core part of this. It specifically guides the agent through 3 distinct phases, matching the human data, smoothly approaching the target contact points on the object.
Getting ready to grab it.
Right. Then engaging and maintaining stable contact once it's made.
Holding on correctly.
And finally, smoothly disengaging, releasing the object in a way that mirrors the demonstration's timing and manner. This structures the learning process around successful interaction patterns.
They also use early termination in training, right? Cutting it short if things go wrong.
Yes, absolutely. It's a way to define a tight feasibility envelope during training. If the character drifts too far from the reference motion, say more than 25 centimeters, or the object deviates too much, like 10 centimeters.
Which isn't very much.
No, it's tight.
Yeah.
Or if contact is lost unexpectedly for too long, or maybe maintained too long after the reference shows release. The episode ends. This keeps the learning focused squarely on accurate reconstructions within a narrow band of acceptable performance. It's kind of a training trick to stop the agent from wandering too far off track and learning bad habits.
And prioritized training, what's that about?
Well, the GAB dataset has sequences of varying difficulty, right? Some are simple, some are really complex. So they periodically evaluate how well the agent is doing on different sequences, and then they deliberately oversample the ones where it's currently failing.
Focus on the hard stuff.
Exactly. This concentrates the training effort on the harder motions, which helps improve overall performance across the entire diverse dataset.
Okay, another challenge. The GAB dataset uses different human subjects, right? Different body shapes, sizes, interacting with objects. That must be a significant hurdle when you're trying to train a single policy on one standard canonical humanoid model. How do they handle that diversity while making sure the interaction still makes sense?
It's a big challenge, yeah. Their solution, which they illustrate in Figure 3, is actually quite clever. First, they use a single average body shape for their target character in the simulation.
Okay, a standard model.
Then they map the local joint rotations from the source human motion capture onto this canonical shape. That part's relatively standard. The tricky part, as you hinted, is the object, because changing the body shape completely messes up the geometry of the interaction. The original hand position might now be inside the object or miles away from it.
Right, because the object isn't just attached to a joint like a piece of clothing might be. It has its own place in the world relative to the hand.
Exactly.
Yeah.
So here's the clever bit. They retarget the object's trajectory too. Using the original contact information from the human motion where the human hand was touching the object, they run an optimization process. This process adjusts the object's global position and orientation in the scene to best preserve those crucial contact relationships, but now with the canonical character's hands or other end effectors.
Huh. So they move the object slightly to match the new body shape, based on where the context should be.
Pretty much. It puts the object in an approximately correct, physically feasible place relative to this new standard body shape. Then the reinforcement learning policy, the mimic manipulator learning in the physics simulation, learns to handle the remaining small nuances and make the contact work properly. It's quite an elegant way to transfer that vital interaction information across different body types.
That is clever. They also filter some motions out entirely, I saw in the paper.
Yes, they do filter some sequences that are just unsuitable for physical reconstruction with their current model. Things like really complex bimanual interactions where that object-centric retargeting doesn't quite work well enough.
Like passing something complex between two hands in a very specific way.
Maybe, yeah. Or interactions that rely on features their simplified body model lacks, like interacting with the face, say, putting on sunglasses, which requires knowing where the nose and ears are precisely. Also, if the retargeted object position jumps significantly between frames, which indicates the retargeting process became unstable, they filter those out too.
Safety first.
Right. So after all this processing and filtering, they end up with a solid training set of over 1,000 sequences and a separate test set of over 100 sequences to evaluate performance.
Okay, so after all that really careful data processing, retargeting, filtering, and that sophisticated reward engineering, how did Mimic Manipulator actually perform? Did it succeed at replicating these complex human motions in a physics simulation?
Quantitatively, yes, it did quite well. As you can see in Table 1 of the paper, their ablation study where they turned different components on and off shows that the tight early termination criteria, the prioritized training on hard scenes, and especially that crucial contact guidance reward all significantly improved performance.
So all those components were necessary.
They really were. And when they compared it to an adapted baseline method, Mimic Manipulator performed significantly better. The authors attribute this, at least partly, to that explicit object structure awareness using BPS, and again, the detailed contact guidance and the reward.
And qualitatively, the paper has some visualizations, right?
Yes. Figure 5 shows some really impressive reconstructions. Pouring tea from a pot, using a hammer, taking a picture with a camera, drinking soup from a bowl. It looks like it genuinely learned these nuanced, tool-specific behaviors. That's quite a feat of physical replication, honestly.
It really is. Does it look perfect, though?
Well, the authors are quite upfront about this. They note occasional uncanny behaviors, particularly around the moments of contact initiation or release. Sometimes it looks a little abrupt or not quite human smooth.
Why is that?
They suggest it might be an artifact of those discrete early termination conditions we talked about. Sometimes maybe forcing slightly abrupt transitions to stay within the good zone rather than the perfectly smooth easing in or easing out you see in natural human motion. But overall, the fidelity is high enough to capture the essence of these complex interactions, which is exactly what they needed for stage one.
Okay, so stage one gives them this high-fidelity tracker, mimic manipulator, that knows how to perform intricate manipulations based on detailed frame-by-frame guidance from human data. That's impressive on its own, but the ultimate goal was versatility from sparse goals, right?
Exactly.
So now for stage two, the masked manipulator itself. How do they take all that detailed knowledge locked inside Mimic Manipulator from stage one and, well, make it generative, make it controllable with just a few hints about the future?
Yeah, that's the core challenge of stage two. How do you distill Mimic Manipulator's expertise into a versatile, generative policy mask manipulator that can produce diverse, human-like, and physically plausible behaviors, but starting from only sparse future goals?
Because sparse goals, like just saying, put the cup over there in 2 seconds, I mean, there are tons of possible ways to achieve them. Right. Left hand, right hand, maybe a transfer. That's a huge space of possibilities. That multimodality, as they call it, sounds like a major hurdle.
Precisely. That multimodality is the key challenge here. Direct training with sparse goals is really difficult because the correct action for any given sparse goal isn't unique. There isn't one right answer to learn.
So what's their approach? How do they handle that ambiguity?
Their approach is clever. They learn from the Mimic Manipulator, the expert teacher from stage one, using an online teacher-student distillation process. It's a technique called DAGGER, which stands for Dataset Aggregation.
Dagger. Okay, what's happening there? How does the student learn from the teacher?
So DAGGER is essentially about training a student policy to imitate a good teacher policy. The student tries to act in the environment, the physics simulation. If it gets into a state where the teacher would have done something different, the teacher provides a correction, the action the teacher would have taken in that state. This helps the student learn how to recover from its own mistakes.
Okay, learning from corrections. But how does the masking part work? How does that create sparse goals?
Right, here's the crucial twist they add for Masked Manipulator. The student policy, Masked Manipulator, isn't shown the full future trajectory from the human data like the teacher was. Instead, it's only conditioned on the current state and a randomly masked version of that future reference trajectory.
Ah, so they deliberately hide most of the future information from the student.
Exactly. This masked version becomes the sparse goal. Maybe it only specifies the target pose for the right hand in 1 second, or the target location for the object in 2 seconds, and maybe the overall body posture. Everything else about the future motion is hidden or masked out.
I see. So the sparse goal, which they call diversital in the paper, specifies targets for only a subset of things, maybe just a hand pose, or the object location, or body stance at one or more points in the future.
Correct. The student, masked manipulator, then has to figure out the full action to take right now,
Sure.
based only on this partial sparse information. But it's guided by what the high-fidelity teacher, mimic manipulator, would have done if it had seen the full, unmasked reference trajectory.
That forces the student to learn to infer all the missing details, right? How to grasp, when to move, which joints to use, based only on the sparse target.
Exactly right. That masking during the dagger training is the key mechanism for achieving versatility from sparse inputs. The policy learns to fill in the blanks plausibly.
And how does it handle the fact that you might give it different numbers of goals, sometimes one target, sometimes five?
Good point. To handle the variable number and type of these sparse goal constraints, they use a transformer architecture for the policy network. Transformers are naturally good at processing sequences of inputs, like tokens.
So they tokenize the input.
Yeah. The input is tokenized some fixed information, like the character's current proprioceptive state and the object state, and then separate tokens for each specified future goal constraint you provide, like hand target at time t1, object target at time t2. The transformer can process this variable length sequence of goals.
Okay. And because of that multimodal problem, multiple valid ways to achieve a sparse goal you mentioned, they explored different kinds of policy architectures to actually generate the action.
Yes, they compared 3 main types, and this is shown nicely in Figure 4. First, a simple deterministic policy. This just learns a single average action for a given input. It might work, but it could struggle with tasks where there are genuinely distinct ways to succeed, potentially leading to less expressive or averaged out awkward motions.
Right, might not capture the variety. What else?
Second, a conditional variational autoencoder, or CVAE. This architecture is explicitly designed to model multimodality. It learns a latent space, a sort of hidden representation that captures the distribution of plausible solutions for a given goal. During inference, you can sample different points from this latent space to generate diverse, varied behaviors that still achieve the goal.
So that sounds promising for generating variety.
It is. And third, they tried a diffusion policy. Diffusion models have become really popular recently. They work by starting with random noise and iteratively refining it over several steps into a structured output, like an action, conditioned on the input state and goal. They are also very good at modeling complex multimodal distributions and generating diverse outputs.
So both CVAE and diffusion are designed to handle that inherent diversity.
Exactly. They were specifically chosen for their capacity to model the inherent diversity and multimodality in the solution space defined by the sparse goals and the human data. This allows MaskedManipulator not just to meet the goals, but potentially do so with varied human-like behaviors that it learned from the mimic manipulator teacher, which itself learned from diverse human examples.
That makes a lot of sense. If the original human data showed multiple ways to, say, pick up a cup, you want your generative policy to be able to reproduce that variety, not just blur them together into something physically weird. So how did these different policy architectures actually perform in the masked manipulator stage?
Okay, let's look at the results from MaskedManipulator Stage 2. Table 2 in the paper shows a task they call teleoperation-style pose matching. Here, the policy is conditioned on near-future goals for the head pose, wrist poses, and the object pose, sort of like mimicking a user's input in real time.
Okay, how did they do?
The diffusion policy actually generalized better to unseen test sequences. It achieved about 58.2% success compared to around 54.6% for both the deterministic and the CVAE policies.
Interesting. Why do you think diffusion did better there?
The author suggests it highlights the diffusion model's strength in modeling complex action distributions, which likely makes it more robust when facing slightly novel situations in the test set that weren't seen during training.
And they also tried training offline, right? Just using supervised learning on saved teacher trajectories without the online dagger interaction.
Yes, and that performed quite poorly, only 25.5% success. This really underscores the importance of that online dagger process, the sort of self-play in the simulation where the student learns to recover from its own errors with the teacher's guidance. Just imitating static trajectories isn't enough to learn robust control.
That's a clear result. What about the other task, Table 3?
Right. Table 3 presents a more challenging long-horizon task. It involves chaining sparse object goals sequentially, where each goal is set 2 seconds into the future. This really tests the system's ability to reason about distant object states, plan complex full-body motion, and maintain stable grasping over longer periods.
So, a tougher test. How did the policies fare?
Similar story, actually. Again, the diffusion policy showed superior generalization performance on the unseen test data, achieving nearly 60% success, 59.6%. The CVAE was next at around 50%, 50.3%, and the deterministic policy lagged behind at 46.1%.
So the diffusion model seems consistently better suited for handling the multimodal nature of these Loco manipulation tasks and generalizing well, especially on harder, longer-term goals. That seems like a key finding.
It really is. And qualitatively, the results for MaskedManipulator are pretty compelling. They show it's quite versatile and can generate some really nuanced behaviors. Figure 6, for instance, shows stable tracking of wrist and head pose goals.
And you mentioned inference earlier.
Yes, what's really interesting is that the policy often infers the appropriate physical contact needed to achieve a given pose goal, even when it's not explicitly told to make contact. It just figures it out based on the sparse goal and the underlying knowledge it distilled from Mimic Manipulator.
That's crucial, isn't it? It's not just trying to match positions in space. It's figuring out the necessary physical interaction, the how, to actually get to that position and stay there stably. It learned that from stage 1.
Precisely. That physical grounding is key. And Figure 7 shows it achieving those sequential object goals we talked about. It demonstrates what they call solution adaptation.
Like what?
Like, if reaching a goal is awkward from the current grasp, it might autonomously decide to transfer the object to the other hand to get a better angle. Or if it's handling a larger object, it might naturally use both hands to support it, even if the goal only specified the object's final position.
Wow, those are complex learned behaviors just emerging from a sparse object goal. It's finding its own way to achieve the goal using its full body and dexterity.
Exactly. It's not just executing a pre-programmed move, it's adapting its strategy based on the physical constraints and the goal.
And Figure 8 shows something perhaps even more surprising. Generative interaction.
Yeah, this is really fascinating. With minimal goals, maybe just specifying a target pelvis position, or just telling it to hold an object without any other specific instruction, the policy can exhibit these emergent behaviors that were clearly learned from the distribution of the human data.
Like the example they show.
Right, like picking up a toy airplane and then spontaneously starting to fly it around realistically. This shows its capacity to generate contextually relevant, even unprompted behaviors that were present implicitly in the vast training data. It's not just a goal achiever, it can actually be a behavior generator, drawing on that rich library of human motion it learned from.
That emergent behavior aspect is a really exciting insight into what these kinds of systems can potentially learn. So, okay, it's powerful, it's versatile, it generates plausible, even emergent behaviors. It sounds like a really significant leap forward. But the researchers themselves also identified limitations, right? What are the remaining challenges or areas for future work they point to?
They do, yes. They're quite clear about the limitations. One is related to the fidelity of the mimic manipulator itself, stage 1. While it's generally good, training a single policy on the entire diverse GRAB dataset means it's sometimes slightly less precise on one specific, highly complex sequence compared to how a tracker trained only for that specific motion might perform.
So the breadth of skills comes at a tiny cost to the absolute peak depth on every single possible interaction.
Potentially, yes. They suggest that the policy representation or network capacity might be a bottleneck for learning such a broad repertoire absolutely perfectly in every single case.
And related to that, it doesn't perfectly reconstruct every motion from the processed data set either, right?
Correct. There were still motions, even in their filtered dataset, that the mimic manipulator couldn't reproduce faithfully within the physics simulation. So there's definitely room for improvement in expanding the range of skills it can capture and reconstruct, especially for new and unseen tasks.
Okay. And what about controlling the mask manipulator, the stage 2 policy? Any limitations there?
Yes, and this is perhaps a key limitation from a user's perspective, the granularity of control. As we discussed, Mask Manipulator infers many fine details, like the specific grasp points on an object, or the precise timing of contact and release based on the sparse goals you give it and the priors it learned from the human data.
Okay, so I can tell it, put the cup over there, and it figures out how to pick it up and when to release it, using a plausible method it learned from observing humans. But I can't easily tell it, say, pick the cup up specifically by the handle using only your index finger and thumb, or release it at this exact microsecond.
Precisely. That kind of explicit user control over those very fine-grained interaction details isn't currently supported by the framework as presented. It generates plausible solutions it learned from the data distribution, conditioned on your sparse goal, but the user doesn't get to manually micromanage how the interaction unfolds at that very low level.
Yeah.
That trade-off between automation and fine control is a really interesting point.
Okay, yeah, that distinction is important. So let's try to wrap this up. This deep dive into the Mask Manipulator paper shows, well, a really powerful two-stage framework for creating versatile, physics-based virtual humanoids.
It really does seem to successfully bridge that challenging gap between needing precise physical execution for complex interactions and wanting flexible, versatile control from high-level, often sparse goals.
And the result is a system that can synthesize diverse, physically plausible, full-body behaviors from these sparse goals. It handles that tricky, multimodal nature of potential solutions effectively, especially using techniques like the diffusion policy and that clever masked distillation training.
Yeah, and this ability to control both the character's body and the manipulated object through a unified interface, using relatively simple goals. It really opens up exciting possibilities. Particularly, you can imagine, for animators and creators in games or virtual reality. It could simplify the process of creating nuanced, believable character actions significantly.
It feels like it's moving towards characters that actually understand how to interact physically, not just being puppets told exactly which joints to move when.
That's a good way to put it. Leveraging learned physical intelligence.
So we've seen how learning from human motion data, combined with these clever techniques for handling physics, multimodality, and sparse goal specification, can lead to these incredibly versatile virtual characters capable of surprisingly complex adaptive behaviors.
It's genuinely fascinating to see how much complex, coordinated behavior can emerge from just sparse goals, provided you've built the right underlying knowledge base from observing human demonstrations within a realistic physics simulation.
But it brings up that interesting question about control, doesn't it? If the system currently infers details like how exactly to grasp an object or when precisely to release it, based on what it learned was common or plausible in the human data, What kind of creative control are we gaining for the user in terms of ease of use, getting plausible defaults quickly versus what are we potentially losing? Losing the ability to dictate exactly how an action should be performed down to the most fine-grained interaction details. Is the inferred most likely behavior always what an animator or designer actually wants?
That tension between leveraging the inferred expertise of the model and providing explicit fine-grained user control is a really interesting frontier in this kind of research, absolutely. How do you give the user the right level of agency while still benefiting from these powerful generative capabilities?
Hmm.
It's not an easy balance.
And thinking about those emergent behaviors, like the toy plane, what other fascinating, perhaps completely unexpected skills or behaviors might emerge if we push the limits, if we train these agents on even vaster, more diverse libraries of human interaction data? If flying a toy plane emerged somewhat unexpectedly from basic object interaction data, what else might be lurking in there, waiting to be discovered?
That's a compelling question indeed. What are the unknown unknowns in the space of learned human behavior?
Definitely something to think about until our next deep dive.